Нельзя.
Hello, we're joining in.
Hello.
Hello, everyone. Let's wait a few more minutes. Okay. Hello once again. There are 16 of us, and I presume everyone is in. Welcome into our distributed ledger technologies lectures. So we'll be doing them twice a week until the end of the term. Some introductory remarks. Today it will be more, I would say, kind of an overview. So we'll try to understand what the distributed ledger technologies are, why they are useful, how they evolved over the time, what are the current state of the art, why they are needed, what we can expect in the future of them. We'll also think about, tell about our plans for the course. So basically, we meet twice a week on Mondays and on Thursdays. About our time on Monday, I presume you got some kind of message that it is 12:50, and we do it 12:50 today. In general, I will need to double check with the Department of Education whether it is going to be all same time every week. So I will keep you updated. your team leader, a student representative, has created a Telegram channel, which everyone will join, and all announcements will be sent over Telegram if necessary. We expect the final exam in the week of, I think, the 11th of December, but all announcements will be made in time, and there will be at some point in the middle of this semi-term, there will be a midterm exam or test or whatever actually we decide to do. Okay, so any questions about, yes, I should probably tell you about the marking scheme. Typically, you can see it in the model, actually, everything is already in the model about that. You'll see the percentage for ABC marks and the composition in, with respect to the final exam, midterm, and labs. Labs are as yet all wide distance learning, and I presume it's going to be until the end of the term, although who knows. Basically, that's it. Any questions so far? Okay. If not, let's start with the real stuff. I believe everyone have heard already about distributed ledger systems or blockchain systems. So 2 questions in this regard. So first of all, whether these terms are completely equivalent, a blockchain and a distributed ledger system, whether it is exactly the same. And secondly, what is actually after? Yes? Yes. So what do you think? Equivalent or not?
Excuse me. Do we supposed to have any visual presentation?
We will. Yes, of course, yes, we will. And it will be, everything we are doing will be recorded and then published on YouTube and a link sent in Moodle. I'm typically using a whiteboard, so we'll be using a whiteboard and we'll be using slides.
Okay.
If in particular because, you know, lots of diagrams, graphics, formulas, that's what will happen definitely starting from the next lecture on Thursday. Today it is more like an introduction, and that's why for today our prime instruments are a discussion and a whiteboard, our best friends. So my first question actually, well, 2 questions. Number 1, whether the terms distributed ledger and blockchain are equivalent. And secondly, the question is whether, well, what is a distributed ledger system or blockchain to that end at all? Please take a few minutes to think about it.
May I? Can you hear me?
Yes.
So the question was if distributed ledger and blockchain are different. Well, yes, they are, because distributed ledger is a type of distributed database, which is simply a list, and blockchain is a type of the ledger, which implies that there is a sequence of blocks that are connected using some hash function, maybe. That's my guess.
I also may guess that distributed ledgers is a bigger set of technologies, but blockchain is a subset of distributed ledgers that has some constraints. For example, it should use some algorithms and some strategies of constructing of its architecture. We cannot hear you.
Okay, apologies for the interruption. So, what is our conclusion? The same or not the same? And what is a distributed ledger system? Could you please voice your answers?
We have already answered, please.
But let's summarize.
Mikhail,
Okay?
please repeat.
Yes, sorry. So once again, number one, same or not?
Not. It's not a kind of question of same or not the same. We thought that it is one is subset of another.
Well, if one is a proper subset of another, then it means not the same.
Yes.
Okay, same means the sets are equivalent. If one is a proper subset of another, then it means not the same. Okay. Indeed, blockchain is just one implementation, one particular way of implementing a distributed ledger systems. Although I can immediately ask a question, of course, so can we provide examples of distributed ledger systems which are not implemented as blockchains? And that would be a more difficult, actually, question to answer. There are very few, if any. So conceptually, not the same, but a vast majority, maybe nearly all distributed ledger systems are implemented via a blockchain concept, which we'll discuss in detail. And then, yes, so we come to the second point. So what is at the end a distributed ledger system as a larger concept? After all, what it is all about? And what the word ledger actually means. Any ideas?
It's like a book of records.
A book, yes. So put it simply, there is absolutely no mystery about that. A distributed ledger system is just a database. Like a book can be viewed as a database containing some data, containing some pages. If you like, you can view the pages as a chain, indeed, because they are numbered through. Then it is a kind of a book. It is a registry book. Actually, a ledger is a term coming from, to a large extent, from real estate management. In all countries, including our country, but it started in the Western world, for example, in England, in the United States. Suppose that there is a real estate, and then this real estate changes owners. It can be sold, it can be donated, it can be inherited. So there is a sequence of owners in that real estate. So a ledger is very similar to a land registry or, uh, well, a cadaster, and there is another term, which actually describes this real estate item, this object, and the sequence of owners who have rights of ownership to this real estate. When the owner changes, then the corresponding ownership record is amended. But what's important is that the information about the previous owners is not lost as a result. So what happens is that there is a full track of previous owners, and now through a certain instrument, in British law it is called deed. For example, a donation is officially called in the British law a declaration of the deed of trust. Then, through this, for example, declaration of a deed of trust, real estate changes owner, and a new owner is appended to the end of the ledger, keeping track and keeping full history of the previous owners. Okay? So that's the fundamental concept behind the distributed ledger systems. Only the original real estate register or ledger, it was not distributed. And in many cases, it is still not distributed. It is just held by a certain governing body, which is a body of trust. And the one who keeps those records is considered to be in a position of the authority. So if there are legal grounds which are verified by that body that the title of ownership changes, then the records are amended, and this is equivalent to registering a new owner. So now it becomes officially accepted that there is a new owner. And everyone could request this information from this governing body, but all those records are kept in just one single place. And up until recently, they were kept on paper. Very recently, maybe until the 21st century. And then you can imagine that there are problems with this approach. Even with the land register, with real estate ownership. What if the records are, for example, destroyed by fire? What if, and it is not completely unthinkable of, what if the official who keeps those records becomes corrupt somehow and illegally and unlawfully alters the ledger? Can it happen? Yes, it can happen. And indeed it did happen on a number of occasions. As recently as it was a rumor which was not confirmed at the end of the day, but as it was publicized sometime in 2014, some kind of paramilitary formations in Ukraine, in Kiev, they seized the office of land register and started re-registering properties, real estates, to their own ownership. I'm not completely sure, whether it was indeed confirmed, because then this incident was denied, but this is certainly a risk. So this might happen. So any centrally controlled database, it has some advantages and disadvantages. In particular, a database which records the ownership titles or any kind of ledger. So basically, for our purposes, a ledger is just a database which keeps track of all its updates. A distributed ledger is a distributed type of such a database. Okay, so what is the difference between a centrally held ledger and a distributed ledger? Let us even think about the following. You have had, I'm absolutely sure already, some database management units in your BS, maybe in the third year or now in the fourth year. Did you? Databases.
Yeah.
Okay. So let's talk about conventional databases briefly first, and trying to contrast them to distributed databases. So, okay, which database systems you are most familiar with?
Relational.
Relational. Okay. So, did you have any programming experience with what? Oracle, Postgres, MySQL, Microsoft SQL? Which of them?
Probably Postgres will be, or MySQL, the most familiar
Yes.
for
Yes.
us.
Great. Because they're open source, they are very widely used, cross-platform, providing good performance. Everything is fine. So, database in that case is a central repository for data. Okay. We typically connect to, let's say, a Postgres or MySQL database. How do we connect to it?
Using a special client application or adapter for some language.
Yes. Why client application? Does this client application need to be on the same machine, on the same host as the database server?
Not necessarily.
Not necessarily. So in fact, we connect to the database using some kind of access protocol. Data requests are sent over the network in general, and the reply containing, for example, the data retrieved by the query are sent back over this network protocol as well. That's why if you make a huge query, then it will take hours and hours and hours for your data to be received. So there is a client-server communication between your database client and your database server over the internet. Okay, that's fine. Now the question is, if we build an application, a database rarely comes alone. A database is typically a backend of a larger application or a larger software system which performs some kind of business application related activity. So how do you think, well, maybe you had any experience building larger systems involving database backends already? So there is a system and there is a database at the backend.
Yeah,
Yes? What was it?
there was various projects. Almost every project uses database as the backend.
Okay, give
Actually.
me one example at least, please.
Marketplace.
Marketplace. Great. Yes. That's a good example. Very good. So basically, transactions which occur in the marketplace are recorded in this database. Let's explore this example. It is a very, very, very good one, actually, because typically transactions in the marketplace, they do not all occur instantaneously. So what happens is that first there is some kind of trading activity. So, for example, it may be some kind of goods market. It could be a financial market. A financial market is called a financial exchange, and actually using various database systems, including distributed databases and distributed ledgers in finance is, you probably already know about this, one of the primary applications of distributed ledger systems. So first, there is some kind of negotiation in this marketplace, and if successful, this negotiation results in a contract, let's say binding contract, between the buyer and the seller about transaction of goods and money. So the seller received the money, and maybe after that, maybe before that, the buyer receives the goods. And all these partial transactions need to be recorded in the database system until the deal is completely closed. So the goods are shipped and received, the money are received, and then this particular trade is done, is closed. So intermediate stages, all recorded in the database, which allow for trackability of our as yet incomplete transaction. Okay, we built a new eBay, a new marketplace backed by a large database system. And then we immediately realize that this database system becomes a single point of failure. So if this database system goes out of order for whatever reason, then your whole marketplace is completely down. And what is worse, if this database contains records of yet incomplete transactions, so for example, money already sent but goods not yet received, then there might be very unpleasant consequences for participants of this trade, because they would no longer be able to enforce their rights. If any track is lost, then it may very well happen that the goods will never be shipped, although the money will already paid, and disappear. So a central database is a central single point of failure. Okay, from your database design, what do we do in order to avoid this? The risk is by far very real. There might be just a disk crash or a host crash on which this database was hosted, a connectivity loss, a data corruption due to either error or some kind of malicious activity, who knows? So the database is really a very, very important backend activity, but it is a single point of failure. What do we do to avoid, in order to avoid it?
Replicate.
Replicate. But have you really had a look at replication techniques in modern databases?
Yes.
How does it work?
We have various shards with the replication set up in the database. So we have various pieces of data spread across our network. And some nodes, I mean, all of them have a dedicated copy that is updated every period of time. Let's say 1 minute, it is synchronized, and all the data across some shard is being replicated among those machines. So if some error occurs, so we will lost only one node, but we will still have enough data to even have a full copy of data, or we will have enough data to recover using special techniques, for example, RAID or whatever technique we use.
Okay, yes. So you see how many different techniques we have already mentioned at that point. So basically replicating a database, as you just pointed out, is a very much non-trivial activity, right? So first of all, yes, you may want to make at the low level, you may want to make your storage reliable, not at the logical level of the database, but just the physical storage. You use, yes, indeed, you use arrays, redundant arrays of identical disks. What array stands for in order to make your storage more reliable. And in that case, your, for example, your array controller is responsible for the data replication. The typical configuration, for example, is RAID 5, very commonly known, which at the cost of some redundancy ensure that the data are fully available, even in the case if some number of those redundant copies fail. Unfortunately, well, if a RAID is within just one host, then you can use, let's say, a modern high-performance RAID SCSI card, and yes, it would work reasonably well. But if your database grows to such an extent that it spans multiple nodes, multiple hosts, and the disks can be attached to one RAID controller, then the situation becomes, even if you still want to do RAID activity, then it becomes a little bit more complex. You may have heard about so-called iSCSI protocol, which is basically SCSI over the network, and using some high-performance network cards, not even Ethernet, but InfiniBand, for example, you can do some kind of RAID activity over the network, and in that case, it scales to much larger data volumes than an individual host SCSI. So yes, it can be managed somehow, better or worse. It can be managed within well, within a single node or across multiple nodes, but probably still within the same data center, because this InfiniBand, it's not internet, it is just a local local cabinet-wide range of communications. This still does not address a number of other problems. So what if, for example, there is a logical corruption of your data? Something is wrong done with your data, the data are logically deleted or overwritten, and in that case, all your replication doesn't work anymore, simply because a valid operation, which is not a failure, would be executed on all replicas. What you can do in that case is to take snapshots, periodic snapshots of your database, maybe really once in a minute or something like that, but that's far too frequent. So that's probably an unreasonable and impossible load on your data. Typically, snapshots are taken far less frequently, maybe once in a day or something like that. And then all transactions for a day can still be lost if there is an incorrect, logically incorrect, but physically valid operation on the database. Furthermore, if you use let's say InfiniBand or iSCSI for your local area network SCSI connectivity, then it doesn't help if, for example, the whole data center, let's say, is destroyed by fire. It's unlikely, a very unlikely event, but not impossible. So who knows? Or by power surge or by something else. Replication across wider area networks is possible. And indeed, that's how, in effect, the distributed ledger systems work as well. But then you typically, you remember that in database systems, uh, we have a trade-off between, and always actually, between several consistency parameters. So it might be that this wide-scale replication is either extremely inefficient, or it will take upon a failure a significant time to recover your data, and possibly not even full of your data can be recovered, or it might be that getting it to a right level of performance is also problematic, because this sharding and all these replication techniques, you need to really balance things like network traffic, data availability, time to recovery, the data size available, and so on. So I would say defining a correct fault model, and that's probably the key point. So defining a right fault model which adequately assesses possible faults and failures in your system, and uh, provides policies to mitigate those risks, so that we know, for example, under no circumstances whatsoever there would be unrecoverable loss of all your data. And if such a loss occurred, then let's say the depth of this loss is limited by whatever, 1 minute, 1 hour, 1 day of operation, but no more. That's a very complex endeavor indeed, especially if your requirement, and it might indeed be such a requirement for uh, dependable transactions, is said that no data must be lost at all. So if logically a transaction, let's say financial transaction, was completed, and the parties who completed the transaction have already received a notification that, let's say, a trade has been done, then it must not be lost in your database system. In which case, your replication model would probably be maintaining several concurrent hot replicas, and then of these hot replicas, one would be uh, the currently master one, and then with some kind of instantaneous switch to a spare replica if the master is going out of business. And again, whether this switch can be made atomic without losing any data, and if losing any data results in legal consequences, for example, for you, that might be unacceptable. That's a big question. So what I would like to say is that, although yes, we do know that database systems, uh, they do provide various replication policies, both actually at the physical storage level and at the logical level, then designing a proper replication policy is a very, very, very difficult task in general. Replication policies and mechanisms. And you really, really need to be sure that the mechanisms you have selected would act adequately in all potential failure scenarios. I'm wondering just if you were doing at some point this type of scenario analysis with your database system. So what can actually go wrong, and how much wrong, and what would be the maximum potential damage if, for example, this or that kind of failure scenario occurs. Did you do anything like that? I
What,
would
what
say
was
if,
the question?
yes,
I didn't get your question, sorry.
the question is, as we pointed out, replicating a database system is in fact a very complex task. So you really need to provide, first of all, some kind of scenario analysis of what can go wrong with your database system and whether your replication model is adequate in order to mitigate those problems. So, for example, a failure of, let's say, one hard drive, if you are using a RAID system, is one thing. But a fire in your data center, which destroys several hosts, is a completely different scenario. Yet another scenario is a logical error in the database system, which without any fire just erases some of your data. And as a result, transactions for the whole day are lost. If we plan for a very reliable database backend, we must really provide a very detailed, mm, call it fault tree, which describes all possible faults and failure scenarios within your system and provides assessment of potential damage. So we know how much data, if any, we can lose in this or that particular case. And my point is, we can't in all cases just rely upon that, our database system provides some kind of sharding and then it is reliable. No, we really need to do very careful planning for it. Sharding would not save your database in case of logical deletion of the data. Sharding may or may not help if all the data, all the shards are located in the same data center and that data center is on fire and so on. So in some, my point is, in real life business situations, when you face severe, serious dependability requirements for your data, you will be required to do very serious, non-trivial scenario analysis uh, for replicas of your relational databases. All right? So it's not a trivial exercise. It
Yes,
is, all right? You agree?
yes, of course.
Non-trivial, error-prone, very easy to lose sight of some potential failures. So you really, really need to be, I would say, a very experienced database engineer in order to plan for such eventualities. So then the question is, and do we really need to do all that? Maybe we would go along a very inefficient, that's true, very inefficient, but on the other hand, very simplistic way. We would not just use some kind of replication or some kind of sharding. We'll run our database in multiple instances, as many as possible, creating an instance everywhere and probably allowing any authorized parties, or maybe indeed, if it is a public one, anyone on the internet create such an instance. The many of them, the better. All of them conceptually identical, so there are no masters or slaves, or let's say hot copies, warm copies, and cold copies in this case. No periodic snapshotting at all, just identical instances, multiple identical instances of our database. That's concept number one, multiple identical instances. And concept number two, in order to prevent logical deletion of our data, then we use databases in which the data are not updated, not deleted, but only amended. you can say that there is a new instance of our data which is more recent than the previous one, but the previous one is still in place. It is never erased. So if at all necessary, then the previous one can be restored for whatever reason, and we can start from that point on. Obviously, if we need to restore it on all connected nodes, then there must be some kind of coordinate decision of the owners of those nodes to do or not to do so. So basically, what we have seen a path from a centralized database. You can see my screen, right?
Yes.
So from the centralized database, we showed that actually distributed ledger is not some kind of invention out of a blue. It is a very natural extension of what we have already been doing, because in the past we would be using some kind of replication protocol at whatever level, and here we would have possibly several replicas, whatever, hot, warm, whatever it means, cold. That's one concept. And from this, we evolve into decentralized, decentralized, decentralized and distributed. A centralized database can also be distributed somehow with replicas, but there is still some kind of central point of control. In this case, there is no central point of control whatever. So all those replicas are completely independent from each other. There are no masters or slaves. Here, for example, this is the master. In this case, there are no. They are communicating all with each other through some kind of, we do not call it replication protocol anymore. We call it an interactive consistency protocol, because they're all independent. It's not that there is a master which we need to replicate somehow and then possibly switch to a replica or recover from a replicas if something goes wrong. No, they're all completely independent. Still, they need their joint state to be converging to something. So they are running some kind of interactive consistency protocol, how we call it. And this is actually distributed ledger. Plus, each of these databases, it contains full history of updates. Thus guarding against accidental altering or deleting the data. So that's simple. And having seen this concept, we naturally arrived at the interactive consistency protocol. The concept of interactive consistency is much older than the concept of distributed ledger. Well, you probably know that the era of distributed ledger systems or blockchain systems to that end started when? When is the birthday of blockchain as we now know it? When do
Maybe
we
we start
celebrate?
about Bitcoin system.
Yes, Bitcoin when? Bitcoin
2009
blockchain.
2000,
or 10.
Which year?
late 2000s, like
Late 2000s. More precisely, 3rd of January 2009. Yes, you're absolutely right. Before that, in 2008, there was a paper, just a manifesto and a very well developed technical white paper by Satoshi Nakamoto on the principles of design of blockchain as a distributed cash system containing the reference implementation. And then the date of the first block going live is the 3rd of January 2009. But interactive consistency protocols, they were known for many years before that, and they were already used before that to a significant success in a completely different setup in real-time distributed systems in real-time control. So because I think this is an instructive example, let us go back into 1980s, and the major inventor, although probably not the first one, but the major inventor and contributor to interactive consistency protocols was Dr. You remember who? Leslie Lamport. Very well known for yet another remarkable achievement. What
Lampard
did...
clock.
Sorry?
Lampard clock.
I'm not completely sure about his clock. What is it actually?
It is a distributed clock. This is some kind of protocol. How can we synchronize a time on various machines?
Well, quite possibly, yes, because a distributed clock is indeed a part of a typical distributed consistency protocol. It might be needed so that they have access to the same source of time if a real time is used for whatever, for timestamping of your transactions. But there is something completely different. So what do we use in order to write technical reports? Which tool? Papers, especially with lots of mathematics.
LaTeX?
Of course, it's his. It's same Lamport. But in the scientific community, he is best known for his contribution to distributed systems. So imagine the following, and to some extent you can see that this architecture, which I'm going to talk about, is a kind of ancestor of a distributed ledger. Only instead of just storing and updating the data, the purpose of this system is to provide some kind of real-time action. Okay, suppose that there is an aircraft, let's say Boeing 777. Okay, why is 777 remarkable? It is the first one which has implemented so-called flight-by-wire technology. What is flight-by-wire? In all the aircraft, the pilots had controls, for example, over whatever actuators, let's say, to deploy the landing gear, to change the angle of the rudder, to change the angle of the horizontal stabilizer, and so on, all the aircraft via hydraulic lines. So basically, the pilot pulls a lever, and that activates pressure in a hydraulic system, and eventually this pressure propagates toward the tail of the aircraft, activating the rudder. So controls of an aircraft were hydraulics. The 777 was the first one which implemented completely electrical and electronic controls. So there are no hydraulic lines anymore. They are in general heavy, difficult to use, and unreliable, in the sense that if, for example, the liquid leaks out of the line, then it becomes unusable. And that's why the previous aircraft would have to use double or triple redundancy of those hydraulic lines. And even then, it would not always be 100% reliable. Flight-by-wire means computer controls, control impulses sent over the internal network of the aircraft to the corresponding actuators, and eventually the actuators acting out of electrical energy in order to do the corresponding action. Let's say deploy or retract the landing gear, or maybe switch on off the engines, or change the rudder stabilizer angle. But obviously, because computers are involved, then you can imagine that faults, software faults, or maybe hardware faults, become a real danger in this case. And the probability of such a danger is no less than, let's say, the chances of your hydraulic lines going out of action. And then in mid 1990s, based on the previous work, in particular of Leslie Lamport on distributed systems, some kind of standard architecture, flight-by-wire architecture, was elaborated, and then it became standardized. There is a standardizing body, American and in fact international, because those standards are widely accepted by many countries, which are called ARINC. And then there is a number of standards governing the architecture of aircraft control systems. So typically the situation is like this. So first of all, in order to do anything, we need to take measurements from sensors, or a particular kind of sensor could be input, let's say input from the pilot. At least sensors and maybe pilot inputs, pilot controls, need to be replicated, just in case if anything goes wrong with them. Definitely for sensors. For example, the most dangerous thing which can happen to an aircraft is a failure or an incorrect reading of the airspeed, of an airspeed sensor. There are at least two very well-known aircraft disasters, which nevertheless, in spite of all those, very well defined ARINC architectures, nevertheless resulted in an aircraft loss with all people on board due to simply incorrect reading of airspeed. Do you remember when it happened? At least two very high profile, more or less recent incidents. One of them happened in the same year, 2009, 1st of June 2009. A Airbus 330 lost over Atlantic. Do you remember what happened? Somehow the sensors froze, all of them, not just one. And that is, how is this called in our computer science terms? Yet there are a number of sensors, yet ice developed in several of them, rendering them all unusable. This is called a generic or a common cause, a generic or a common fault. They're rare. Nevertheless, it happens. A failure of a particular sensor is not that rare. That's why this hacking architecture calls for triple redundancy. So, for example, we have 3 sensors, and then there is an onboard computer which takes reading of all those sensors. This computer by itself is not just a single processor. Typically, it contains several line replaceable units inside, communicating over the internal backplane bus. So they're all communicating with each other. And actually, input from those sensors is directed into all those line replaceable modules. So they perform voting, 3 version voting on the data received by the sensors. Each of them is performing the corresponding calculations. For example, whether we need to adjust, I don't know, engine thrust. So then there is an engine here. And there is an engine control block. Each of these units sends individual output to the engine control unit. And there is an N version, in this case, N is equal to 3 version voting in the control, engine control here. Because it may very well happen that a corresponding, a single computing unit can also become faulty or become out of action. So that's a typical way of how this redundancy is implemented. The units, moreover, these 3 line replaceable modules, as I put them, they are located in a certain cabinet within the aircraft. But what happens if, you remember our discussion of a database replication, what if this cabinet itself is destroyed, possibly by some kind of, let's say, physical damage or enemy action or whatever? Then the cabinet itself is probably replicated as well, maybe not with triple, but at least with double replication, but still. So then the inputs from the sensors are fed into those line replaceable modules as well. And then there are more outputs coming to the control and voting is performed on them. There are several standards for the backplane bus used for communication of modules within the cabinet and aircraft-wide bus, which is, for example, called ARINC 629 standard, if I remember correctly. And it is a kind of token ring bus, not Ethernet. So this type of architecture. Okay, can you identify some very interesting logical issue with this type of architecture? So one thing we have already identified, so 3 version voting. Moreover, at that voting, moreover, at that time, it was also a standard to implement software within those line replaceable modules, for example, 1, 2, and 3, using, it would be same spec, but 3 different implementations written by 3 different teams compiled into machine code using 3 different compilers, and moreover, to remove the possibility of a hardware failure within a CPU, it would typically be 3 different CPUs even. So for example, one would be our classical Intel x86, number 2 would be Power, and number 3 would be Spark. No doubt you have heard about them. All right? No, I think Spark with C. Yes. Spark with C. Okay. Still, we need to do voting on data coming from the sensors. Later on, we need to do at the engine control unit, we need to do voting on multiple outputs generated by multiple processors. What do you think? What do you think is an issue here? What kind of problem we'll be facing immediately? A logical one.
What is the failure is in engine control?
Oh, sorry?
What if the failure will be in engine control?
Well, yes. What if the engine control here fails? You are absolutely right. This is a single point of failure, by the way. And unfortunately, the engine control cannot be entirely replicated. Maybe some parts of it can be replicated as well, but eventually there is just one output coming into the engine, because at some point, yes, as you would understand, yes, all voting is already done and there is one single consolidated action going into the engine control. Yes, it may happen. It is a single point of failure. If that happens, the engine is out of action. Fortunately, our aircraft has at least 2 engines, and each of them is powerful enough so it can continue the flight to the nearest airfield, even if one engine flamed out or is out of control due to whatever reason, in particular due to the engine control unit failure. But you're absolutely right. So then the only replication we have is that there are fortunately 2 engines rather than 1. The whole system would become completely useless if our aircraft has only 1 engine. Okay? Now, still, logically, what is, I would say, very much problematic here? Yes?
Are there only 2 possible outputs for the engine control, or more commands can be sent to it?
Could you please repeat the point?
Are there only 2 commands that can be sent to engine control? Or, for example, we have at least three different commands that can be sent to it.
The commands sent to the engine control, they have some types. So, for example, start, stop, to put it very simply, increase thrust to a certain level, decrease thrust to a certain level, things like that. So they are obviously typed, and yes, you are very close to the problem. So you see, let's even start with the sensors. How do the sensors send readings to the processors? Actually, each sensor is a small computer by itself. It is a very, very small embedded system which implements some kind of periodic reading. Not that much extremely frequent. So typically, let's say 100 hertz, 100 times per second is about the maximum, possibly even less. You don't need that much. Maybe some less important sensors would be read only at 1 hertz. So there is some kind of embedded, very small embedded controller, which simply performs a reading with the frequency from 1 to 100 hertz, and when read, it sends a message, well, a number of messages to all those processors over the network. And this network, outside of cabinets, aircraft-wide network, is, as I said, it is a ring type, a ring 6 to 9 token ring bus. So what does it mean? Conceptually, it means that the communications are not instantaneous. It's not that the message propagates immediately, just with the speed of light, and immediately received by the processor. What happens is that, what is token ring? You probably know that there is a certain period, and within that period, temporal slots, are allocated to all devices on the token ring. Within that temporal slot, a device can publish a message on the bus, okay? When the time is right for it to publish, which means that, by the way, the clocks of the devices need to be synchronized, but that's probably quite easy because the bus itself can carry synchronization impulses. It's not internet, it's a local bus. So the time is right for this sensor to publish information. It publishes. And at that time, the CPU reads this information. Then the next CPU would probably read it at the same time if connected to the same bus, but the next sensor publishes in the next slot. So the messages are not even sent at the same time due to this architecture of the token ring. With Ethernet, for example, there is no such a requirement to send at the same at dedicated times, but you know that in Ethernet messages can be lost. Precisely, it is hardware detected. If two devices publish at the same time, then collision is encountered and messages are dropped. For high dependability environments such as uh, aircraft data buses, loss of messages is deemed to be unacceptable, and that's why token ring is used instead of Ethernet architecture. It is slower in general, but it is at least guaranteed that each device has its own slot to publish information, and there will be no clashes between them. So the messages are published, and the messages arrive at CPUs at different times. Well, for this CPU, for example, well, for the messages coming from the sensors, it is probably possible to estimate the maximum discrepancy between the messages, because after all, if all of them are published at the same time, then the only discrepancy could be due to different positions in the token ring when a sensor is allowed to send a message. But now imagine that on those CPUs, there is a hierarchy of tasks running. So it's not just a single, some kind of single program running in the infinite loop. No, there are multiple tasks. Apart from those sensors, there are many other sensors which publish information, and this information is received by, in fact, different tasks within those control units. As a result, this information is processed already at significantly different times. And when outputs are sent to the engine control, then they all arrive completely out of sync. So for example, a certain message came from CPU 1, but what does it actually mean? Was it acting on input at what time? it might be that the engine control has received, for example, if we have 6 CPUs altogether here, they received outputs based upon, well, 6 outputs. 5 of them are based upon one instance, or at least, related instances of time for the sensors to read the information. And another one received yet the previous one. What is the correct way of performing voting in this case? If your data which you receive may actually belong to different generations of data, or even the whole notion of a generation is not completely well understood in this case. So we immediately arrive at the concept of an interactive consistency protocol. We need to take into account somehow that the data which we are receiving might be asynchronous, attributed to different times, and yet we need to make some kind of consistency between them. What do you think? How do we solve this problem, this kind of problem? It was a very much real problem in the design of distributed real-time systems, and the protocols developed to that end were the predecessors of interactive consistency protocols in our contemporary blockchain technologies. Actually, many of them are drawn from 1980s, 1990s days. Any ideas?
We could probably mark each message with a timestamp using some clock.
First of all, yes,
like
you are
Lamport
right.
clock.
First of all, you are right. So each message is marked with a timestamp, and actually what we need to do is to mark them with the origination timestamp. So each message is marked with the timestamp corresponding to the oldest data which were used in order to produce that message. Not the newest one, the oldest one. And then we can still, by the way, this is not a very easy task either, but we can calculate and bound from above the maximum delivery time of a message from the sensor to the actuator. So this is actuator. How? Everything is predictable. If messages are delivered by by token ring, then we know the maximum period or how many periods it would be required in order for a message to get its slot and to get delivered here. Here we have control units and real-time tasks running on those control units. A real-time task, what is a real-time task or real-time process?
It is a process that has some deadlines.
Which has a deadline and which has a guaranteed response within that deadline. Yes, absolutely right. So real time doesn't mean fast. It means with guaranteed deadline. Or at least if it is a so-called hard deadline real-time process, then yes, it has a deadline, and the scheduling policy of those processes is guaranteed to meet the deadlines. It is verified somehow. It is a very exciting theory on its own. Some elements of it are relevant to our distributed ledger system. Some of them are more relevant to building control systems. If you did not have real-time theory or real-time operating systems yet, maybe you will still have them in the next term, or maybe not at all. We need to double check, but it is a very, very important, relevant, and interesting theory by itself. So basically, because you see the schedule of sending messages and schedule of invocation of tasks which process those messages and then send them further, they're all very much dependent on upon each other. Yet, this is so-called holistic scheduling. Yet there are methods which do allow you to provide the ultimate response time. So suppose that between
Excuse me.
yes,
May I ask you a question?
yes,
So I have a question about a timestamp. Why do we need to use the timestamp of the very first event that triggered something, some action, or you said something about it? So we
yes,
don't
I
need
was
to.
just about to approach this point. A very good question. Yes, just a minute and you will see why. So suppose that there is a T capital, which is the maximum absolute upper bound for the delivery time for a message from the sensor to the eventual engine control actuator. So from our schedulability analysis of our communications and tasks, we know this upper bound on T. Okay. What would the engine control do in this case? The engine control would not immediately act upon all messages. What it would do, each message is, apart from a timestamp, each message, of course, has a version. Where is it coming from? From processor 1, 2, 3, and so on. So suppose that there is a P1 queue of messages, P2 queue of messages, P3 queue of messages, all messages coming from different sources. So what would this voting engine within the engine control do? They would stockpile messages at each time, keeping them, so it has access to real-time clock as well, keeping them up to depth T into the history. So, for example, the new messages in front, but all the messages in the back of the queue. And then what we can say, that if the time T elapsed, then we are guaranteed that all data originated within that time T from now, and that's why the oldest timestamp is important, actually. All original data are already in and have already been processed, and we can do voting on them. So basically, we select the newest item in our queue. We select the newest item, which is at least T seconds old. They could be even different within our network. So in that case, we know that these are the data which have already for sure been processed and conceptually correspond to the same originating time, irrespective to when it was really delivered. It may have been delivered earlier than that, it doesn't matter. It has an originating timestamp, which is the latest one, the latest of the earliest within this time horizon. Between them, we perform voting. If you want to know more about this algorithm, because what I have described is only a scheme and not an algorithm, I might be able to provide you with some further details on that. So it is the boundness of our time to communicate, which is the foundation of the consistency algorithm. So we vote on the data, which are for sure using the fully processed inputs, because the maximum time required for processing of such data have already elapsed. This is an example of an interactive consistency protocol. Something like that is happening with interactive consistency protocol in blockchain. For example, in Bitcoin's blockchain. Because actually we'll study this protocol in very much detail, but it is important to understand that new blocks, which is similar to new messages in the engine control actuator, are produced not that frequently. There is a deliberate delay, so that, for example, in Bitcoin, one block is produced on the average over 10 minutes. 10 minutes not only because producing or hashing or signing the block requires proof of work, and that's a very, I would say, expensive computation, but also because 10 minutes is probabilistically, of course, unlike T capital here, which is an absolute guarantee, but 10 minutes in blockchain is a probabilistic but still a very high guarantee that all data from which this block would be supposed to be composed of have already had a chance to propagate through the network, even into very, very remote locations of the internet. Because for that, typically, let's say 500 milliseconds are enough, not just 10 minutes. If this time becomes comparable with the time of network propagation, then the probability of inconsistencies caused by propagation error, propagation delays would become much higher. The interactive consistency protocol for Bitcoin's blockchain and other blockchains, they have mechanisms to deal with such inconsistencies. And yet, it would become much less efficient, at least, if the probability of these inconsistencies due to network delays become much, much higher. And that would happen if the network propagation time is comparable with the average block signing time, block hashing time. So in this case, the system is probabilistic, still probabilistic. So as you will see, the interactive consistency protocol here, it has some probability of, I wouldn't say of a failure, but of a splitting the state into, let's say, inconsistent states. But in the way of how it is designed, this probability is infinitesimally small and can be tolerated. In flight control systems, it must not be probabilistic because there are far less nodes here. So here there are only 6 or maybe even 3 nodes. So a probability of inconsistency must be ruled out completely. And that's why we use token ring here with an upper bound on propagation time. Whereas for Bitcoin, do you have an idea actually how many of fully active hashing Bitcoin nodes are currently in operation? Everyone can start a blockchain, for example, Bitcoin blockchain node, but you would typically use it as a listening node only, not as a hashing node. Because for hashing node, well, in order to get some kind of success in hashing, you need a very powerful mining equipment nowadays. So how many fully hashing nodes of a Bitcoin blockchain do you think operate simultaneously on the network, on the internet? Just by the order of magnitude, let's say 100, 1,000 more, maybe 1 million.
On the internet, they say it's more than 1 million.
Unfortunately, not so. 1 million is, or more than 1 million is the total number of nodes, including non-hashing ones. Listening nodes are also included. Fully hashing nodes, not that many after all. It is about 10K, maybe slightly over 10K. Not that many. But still, 10K is by far a greater number than 306. And that's why probabilistic algorithms are okay here, but they would not be okay in interactive consistency protocols for aircraft control. Here we have full schedulability analysis and the absolute upper bound for T. Here we have a reasonable, by far reasonable T equals to 10 minutes, although not guaranteed, whereas it is guaranteed here, and probabilistic algorithms working over 10K, let's say, hashing nodes in this case. How this algorithm works, we will consider next time. So I will finish this lecture with just a very brief to remind you timeline of very important events which occurred in blockchain development. So 2009, Bitcoin. 2010, what happened in 2010? There was the first and only so far fault found in the Bitcoin interactive consistency protocol, which would allow for actually invalid transactions to be recorded on the blockchain, which resulted in a code base split at that time, but it never happened since then. It did happen many more times with other blockchains, but it happened only once with the Bitcoin. 2011-12. Well, Bitcoin, as we know, it was created for the only purpose. So it is not a general purpose blockchain. The only purpose of this blockchain was to provide a digital cash, BTC. Bitcoin is a digital cash. So BTC takes real value. So it starts really exchanging to US dollar, for example. In particular, through the year of 2013, it increased from about, if I remember correctly, 30 at the beginning of the year to over 700 at the end of the year. But the first financial transactions involving BTC, they already occurred in 2011 and 12. So this digital cash really started playing the role of a real cash, which is a means of payment, a means of accumulating wealth, especially, you know, it is a very good thing if it appreciates that way, and a means of financial trading. Well, not all of them at that time, but at least a means of payment. It was already at that time. It was blamed for being used primarily for illegal and illicit payments at that time. So this infamous infamous dark net site, which was called Silk Road, which was eventually closed down by FBI and the owner arrested. It started using BTC as a means of payment in around 2011. Then, so this is all related to BTC. By the end of 2014, Vitalik Buterin conceived the Ethereum network with the main difference. So what is the principal difference between Ethereum and Bitcoin? Is that the Ethereum blockchain is capable not only of performing digital cash transactions, but it introduced the concepts of scripting virtual machine, scripting, and therefore what is now called smart contracts. Implementation was finished in mid 2015. In 2016, there was a major mishap again, a vulnerability in Ethereum, which resulted in a split. So what was called Ethereum Classic was split, well, remained Ethereum Classic, but currently it is ETH currency, because after a major theft of $50 million and a decision, we say in blockchain systems, the future is immutable. It is not possible to revert transactions. They remain in the system forever. Well, not always. By a consolidated decision of all developers, the future was left behind with ETC. A code fork was introduced, which was not backward compatible, and a new digital currency, a new incarnation of Ethereum called ETH, was developed at that time. It was July 2016, in order to devalue the stolen assets. So the stolen assets, they were stolen, but they became ETC, where the majority of Ethereum moved into ETH. Then 2017, you know, it was the major hype frenzy, call it either way, with BTC USDT or USD up to 20K. Lots of ICOs, lots of all new coins, most of them implemented at that time on the Ethereum blockchain. And about 2016 as well, the development of other general purpose blockchain systems, for example, a family of Hyperledger, started, which is really a general purpose distributed database rather than a blockchain primarily carrying monetary transactions in digital cash. Actually, even Bitcoin is capable of a very simple type of scripting. So a very rudimentary smart contracts are available even in Bitcoin. Full-fledged smart contracts, but still with the primary purpose of running digital currencies, ETH or whatever, are available in Ethereum. In the next generation, so let me call Bitcoin the first generation, Ethereum the second generation of blockchain technologies, Hyperledger the third generation, because it is a general purpose blockchain technology, not necessarily linked to monetary transactions. So now the world is in this third generation, which finds a large number of applications not at all linked to financial ones. Although these digital cash applications are still by far important, the total capitalization of cryptocurrencies reached 800 billion USD by the end of 2017. It then dropped when the frenzy went out, but it is still about 350 billion currently, which proves that, you know, proves to all skeptics that those digital currencies, they are not a pyramid. They are not worthless of money. They are not a kind of, maybe you have heard about that, a kind of MMM pyramid, which occurred in Russia in 1994. Not at all. They do have intrinsic value. And that intrinsic value is precisely because they serve as digital money, as a means of payment, in particular trans-border payment, with much less commission than your typical bank would charge you, as a mean of, yes, storing the value, because the price has now more or less stabilized. It is volatile, but at least we know that it would not fall to zero. As a means of trading and making possible investments. So it is a publicly generated, publicly issued, independent of any central body, uh, digital money. We'll talk about digital currencies and regulations and the future of that, maybe at some point in the future. But the point to remember is that BTC is still #1 digital currency. The Bitcoin blockchain is very much operating, obviously, and it still carries more transactions than Ethereum and other public blockchains together, typically. But for non-monetary transactions, general purpose blockchains like Hyperledger are taking upper hand. And I dare to say that in the year 2020, maybe the fourth generation of blockchain is under development. And you know, where is it under development? By whom? By us in Annapolis. Here, we have a leading research center in blockchain technologies established this year under the government grant. We are developing InnoChain, a new distributed ledger technology, which is based upon the notion of formal verification of all the software involved. So faults like this 2010 fault in the consistency protocol of Bitcoin, or this incident in 2016 with Ethereum, or many other mishaps would be ruled out by construction due to formal proofs of correctness, security, and other dependability properties which we prove in this construction. So at some point we'll discuss them, but this is an overall picture for you. By the way, this module is about blockchain technologies. There will be one more, and I will encourage you to sign for it, more about programming of smart contracts. So smart contract programming in depth, which is going to be in the spring term next year. We'll cover, obviously, smart contract programming here, but in more detail, it will be in your final term. That's all for today. That's an overview. And in the next lectures, we'll first of all, we'll need to be concerned with cryptographic protocols, which are used as means of securing those interactive consistency protocols in the big, wild internet environment. So we'll study digital signatures and in particular elliptic curve digital signature mechanisms. And then we'll discuss Bitcoin operation in detail. We'll discuss Ethereum. We'll discuss its virtual machine. We'll discuss smart contract programming. And we'll discuss third generation and maybe even fourth generation technologies as well. So that's our plan for the rest of the term. For today, we're done. Any
Sorry,
questions
can I
from you?
have? Yeah, I have a question.
Yes.
Isn't it's just that is interactive consistency problem the same as consensus?
Oh, yes. You can call it consensus, yes. These two terms are equivalent. Interactive consistency and consensus are used interchangeably.
Okay, thank you.
Thank you for reminding me of that. I myself came from a real-time systems background, and that's why I more typically call it interactive consistency protocols. Of course, you're right. Okay. So, thank you for attending today's lecture, and we meet again on Thursday. We'll be talking about cryptographic backgrounds used in blockchain systems.
Thank you.
Thank you.
Thank
The
you.
video will be on Moodle. Thank you.